Good morning, welcome to this lecture. My name is Alessandro Golkar. I'm an assistant professor at the Skolkovo Institute of Science and Technology. And this morning I would like to talk about this lecture on what is system architecture and why it's important for the development of complex engineering systems in space. All right, let's talk about number 3, evaluation. So let's assume now that we enumerated the architectures we need to enumerate, and now we have to evaluate them. Now, what does it mean to evaluate them? This is step number 3 in the framework. Tree space evaluation is the process of ranking architectures across multiple metrics. And the goal of evaluation is to provide quantitative measures of merit to support the subsequent down selection of concepts and your recommendations to decision makers after you do the study. And metrics in a sense are a measure of how good, how expensive, how risky are your alternative architecture concepts, right? So you can define some metrics for performance, you can define some metrics for cost, you can define some metrics for risk, okay? And there are many other metrics you can think about. Mainly this is what people in the system engineering research community call the ELITs, right? So reliability, flexibility, interoperability, scalability, and so far and so forth. All these things have to be considered for a full evaluation of trade spaces. Now, how objective are evaluation metrics that you choose? We as engineers are typically trained to deal with measurables, so objective metrics, right? We can use sometimes some proxy metrics to measure some attributes of interest. So for example, to measure, I don't know, if you want to measure the impact that your project has on media, you can measure the number of press releases per day that are released, right? So that's an example, right? These are what I would call objective metrics. So things that measure things like goodness, performance, expensiveness, things like cost, and riskiness, risk. For example, data rate, power throughput, teraflops, all these things are objective metrics. Now, system engineering, I would say modern system engineering, what the International Council of System Engineering called the Vision for 2025, if I'm not wrong, on system engineering. It's about also to consider subjective metrics, to measure non-measurables. In what is called model-based system engineering, you want to measure social and political implications on your system developments. So things like impact on population, societal value, science return, right? So there is always a vivid debate about those arguments, because those metrics are not very precisely defined. They can be ambiguous, they can be biased, and all things of the like. But unfortunately, they are required because systems are needed to fulfill societal needs, and therefore you have to measure societal impact sometimes. There is a concept that is very dear to me that I wanted to share with you. Is the concept of iron triangle. So, as I mentioned before, there are 3, let's say, main categories, right? If you exclude the ELITs, you have performance, cost, and risk/schedule. The concept of iron triangle means if you want, in your system development, you can fix performance and cost, but you cannot fix risk. Or you can fix performance and risk, but you will not fix cost, right? So there is really always some degree of freedom that you have to manage carefully. And as said, there are 2 types of metrics in this main characterization: objective and subjective. Let's talk of the let's say interesting ones, subjective metrics. How do you measure, for example, science return of an exploration mission? How do you measure impact on the media of some outreach program? How do you measure I don't know, satisfaction of your government stakeholders? Well, a way to do it is to use utility theory. Utility theory was originally formulated and used in economics to represent the satisfaction of economic agents, right, in several different theories. In this context of system engineering, we can use them to measure value, right? It's one way. I'm not saying it's the only way, I'm not saying it's the perfect way, I'm just saying it's one way Typically, those utility functions are unit normalized, so they go from 0 to 1. They are bounded, therefore, and so this idea of having a bounded utility function is also a limitation, because sometimes there is some value attributes that cannot be bounded. They describe value that is delivered to an individual stakeholder or a group of stakeholders as a function of the design vector. So, for example, if you have a utility equal to 0, it means you have no value delivered. If you have a utility equal to 1, it means that you have full value delivered. This is how utility functions work. How do you measure those? How do you measure, for example, the utility function associated with, let's say, science return? The typical way to do it, proper way, is to use the so-called lottery equivalence. Okay? Now we'll explain what it means. Step number 1, you assume a function of the utility function, right? So is it linear, is it negative exponential, is it convex Cobb-Douglas function, and so forth, right? And step number 2, you will determine some of the points on this utility function using lottery equivalence. Here's the method on how you can derive lottery equivalence. Step number 1, you assume a shape for the utility function, whether it be linear, for example, value associated with number of samples you retrieve back from, let's say, Mars. Typically, if you talk to a scientist, he would say the more the better. And as you can see here, the model just suddenly breaks, because if you want to use a bounded function, as I said before, you know that there is never going to be a full satisfaction, right? But using a linear function, it could allow you to do so. If you want to go back to the paradigm that I was mentioning previously, having a bounded function, you can use the so-called Cobb-Douglas function, power function, or negative exponential, things of the like. Then you have to interview your stakeholders to determine, let's say, what are the points for which this utility function is going to be, let's say, 0 and 1, right? So the limits, the bounds. And then let's say you take the intermediate point, 0.5. So how do you associate the value associated with that mid value, mid 50%? Well, you put the stakeholder in front of two lotteries. The first lottery says there is a 50% chance that you're going to get some outcome x2, right? So the best outcome, the one to which you associated 100%. And there is a 50% chance that you're going to get outcome x1, the one to which you associate the utility value 0. Right? And you say, now I'm going to give you another lottery in which there is a p probability to get xi, okay, so some intermediate value, and there is a 1 minus p chance to get 0, so the x1, right, so the lowest one. And you ask them, what is the value of p for which those two lotteries are equivalent to you? And once you have this p, you can write down the balance equation, basically that the expected value of one is the same as the expected value of the other one, and therefore you will find what is the utility associated with point xi, which is the one you're probing, right? Which could be a mid value, for example. And by doing so, you estimate another point, right? So now you have point 0, point 1, you have utility associated with xi, with the mid value between x1 and x2. Then you can define other midpoints, right? And by continuing to do so iteratively as much as you want, you will define the shape of a utility function. For example, if you're choosing a shape, then you can fit the shape to those points. Now, this method I've just shown to you is good for single parameter, single variable utility function. So utility function that depends on one parameter. Of course, in reality, sometimes you may want to have multivariable utility functions. These have been subject of academic research, especially in the economics field, for 30 plus years. I don't want to comment more on this. It's really a fascinating but long topic to explain. If you want to know more about it, you should refer, for example, to a seminal work made by Keeney on multiplicative utility functions. And here I want to mention there's this article on the Operations Research Journal, volume 22, number 1 from 1974, which is going to be the start of a long study session for you if you want to know more about it. Here I'm sharing with you a slide that shows a typical utility function as elicited with an expert for one of the studies I've run in my research group. Shows, for example, the value associated with the total number of samples retrieved on Mars. It goes from 0 to 1. And as you can see, you can also associate uncertainty bars because you can pose similar questions in other forms using other types of lotteries, and therefore you can associate the uncertainty with the measurement. What I've just talked about has limits. Utility theory is not perfect at all. Sometimes this concept of lottery equivalent is very awkward, both to formulate and to try to explain to experts. For example, what is the probability P that will make you indifferent between choosing investments in conventional or renewable energy sources? It's a really hard question to answer, right? So, and sometimes experts have a hard time to understand you and to answer you properly. Other thing is that if you look more into the multivariable formulations, they are typically subject to several constraining assumptions. So, for example, there is no utility switch allowed. I'll give you an example. Let's say that your multivariable, it's something that has to do with performance and cost. Now, there are some cases, for example, if you have a high budget, your ranking, your priority among attributes is going to be 1. But if you have a low budget, maybe your ranking changes because you have a low budget, right? And so this could lead to, very complicated utility functions. Maybe sometimes they're not functions at all. So this is a limit to utility theory, traditional utility theory. Of course, there is research that has in part solved this problem, in part is solving these problems, right? And sometimes, especially if you go into the research products of utility theory, these are very sophisticated functions which are very cumbersome to implement, to interpret, to explain to experts. So there is a lot of limitations on this theory, but it is one good theory. Now, there are other ways in which you can do subjective evaluations, for example, surveys, associated scores using Likert scales. I'm not going to comment more about that, just to say that, for example, in the field of social science, you will find many tools that you can apply to system architecture for trade space exploration. Now, I would like to share with you a couple of principles on what makes good evaluation metrics. Principle number 1 is that your evaluation metrics must be a function of the decision variables contained in your architecture vector. If it's not the case, then it means you don't have a proper formulation, right? Or either the evaluation metrics are not properly formulated, or the design vector is not properly formulated. Principle number 2 is that evaluation metrics should be as much as possible independent from one another, so they add information to the analysis, and they should be conflicting. Otherwise, there is no trade-off, right? If you take a metric that one is proportional to the other, then it means you're not doing a good job in finding your good evaluation metrics. Some example of dependent metrics in space. Sometimes people estimate cost using parametric mass models. If that's the case, it doesn't make much sense to put mass and cost because they are related by definition, right? On the other hand, an example of conflicting metrics, for example, for satellite systems, is to try to maximize performance while minimizing cost. Now, you may want to architect for ilities. So you want to consider what people call the downstream and upstream influences in the architecture. And this results into the evaluation of several ilities, such as reliability, sustainability, affordability, and so forth. And they can be evaluated in many different ways. I just want to point out that there is a whole research community that looks into this type of problems. You may want to look on the web for additional resources on that. Last point of the talk, with which I want to close this second part, is down selection. So assume that now that you formulated the trade space problem, you enumerated all the possible architectures available, and you evaluated them. Now it's time to choose, right? To choose which ones you want to carry forward in the analysis. And how you do this? Well, one way to do this is using the so-called Pareto optimality criteria. So the point of Pareto optimality is to say, from this whole bunch of things that they have available, that they have evaluated using different metrics, let's find the ones that give you, informally saying, the best bang for your buck. So basically, that give you the most performance for that level of cost, right? And for each level of cost or utility or whatever the metric is, you would find a frontier of Pareto efficient solutions. There is a mathematical definition for that you can implement to an algorithm, and that allows you to find from a set of options for which you define the evaluation metrics, you define if you want to minimize or maximize them, you will find the Pareto solutions. And the meaning really is to find the best trade-offs, the most efficient trade-offs in your space, and this will give you a set of options. So as a result of this method as applied to multiple evaluation metrics, you will not get one answer, because there is no absolute optimum. There is a set of optima, depending on what is your ranking, for example, of the different evaluation metrics, right? So you will be able to give to your decision makers a variety of alternatives which are useful to you. So typically, especially in economic analysis, Pareto optimality has been studied for cases in which this Pareto front is convex, which is a nice mathematical property that allows you to formulate theorems and postulate things. Problem is that in engineering, when you do this thing in real-world systems, most always the case is non-convex front, non-linear, the nastiest thing you can think about. So typically, you have to find out this front, with heuristic methods or by full enumeration. So once you identify a Pareto front, you can analyze it as it was, it's a space where you can define regions. Typically in a Pareto front, as you can see in the chart, there is an area of low performance, low cost solutions for which a small increase in cost is going to give you an incredible, well, not incredible, but let's say significant increase in performance. There is an area of what I call the best bang for the buck, so basically an area in which there is a fair return for your investment. And then there is an area for high performance, high cost, which means if you want to get that last % of performance, then you will have to pay a lot of money, right? And as you can see, this Pareto front, as is shown here in the chart, it looks at a utopic point, an utopia point, which allows you to say, this is kind of an attractor for your best solutions. It's a way to interpret your trade space. Other things to learn, well, first of all, what are the boundaries of the regions in the Pareto front? There is no exact boundary, right? So there is no exact definition where to define these regions, but they can be found, let's say, visual inspections. You can define some mathematical properties if you want, but typically they are arbitrary, criteria to determine which region is which. Which region would you choose? Well, typically people tend to choose the ones that are close to this kick, to this region where a fair returning cost corresponds to, fair investment corresponds to a fair returning performance. So this is typically the region where good solutions are for the design. So from your analysis, you assume you will find the Pareto solutions. You can choose some from the Pareto front, and these are the ones you want to carry forward. This is really the goal of your trade space exploration exercise. So to summarize and close this part 2, what you've seen here, what I've tried to convey is an introduction to trade space exploration, to understand the purpose and learn fundamental approaches of the discipline as part of the life cycle management process, very early in the design stage where you have to take decisions. These are tools that allow you to support your work, really. They don't make the work for you, but they support in your decisions. Then we applied trade space exploration to support formulation and selection of system architecting problems, right? And I hope I gave you a good introduction on how to properly formulate a trade space exploration model. So with this, I would like to close, and I would like to invite you also to check online resources on this website, on Skoltech website, on OpenCourseWare. For there is a lot of material out there in the scholarly community if you want to know more about trade space exploration and system architecture. Thank you very much.